Horizontal scaling is the standard design pattern for building elastic, high-performance cloud systems. By simply distributing workloads across multiple compute nodes, you prevent any single machine from becoming a resource bottleneck. But this creates an immediate operational challenge. Multiplying identical compute nodes is useless if incoming client traffic cannot be evenly distributed among them. To solve this, you need a dedicated traffic orchestrator, a load balancer. Without this centralized load balancing layer in place, parallel compute resources remain disconnected islands, unable to serve collective user demand. You have two options for this layer. The first is to deploy a self-managed load balancer by installing software like HAProxy or Nginx on a standard EC2 instance. At first glance, this approach looks attractive because of the low hourly compute costs, but that ignores the operational tax it places on your engineering team. You must manually handle operating system provisioning, software patching, and configuring high availability across multiple availability zones. The fatal operational flaw of this self-managed model is capacity. Your engineers must manually scale the load balancer itself to prevent the proxy from becoming a single point of failure. The alternative is the Elastic Load Balancer, or ELB. This is a fully managed AWS service that eliminates these specific burdens. With an ELB, AWS provides a binding SLA guaranteeing the availability, scalability, and underlying physical maintenance of the load balancing nodes. As an architect, you are only responsible for adjusting a few minimal configuration knobs. You simply define the routing protocol, set the listener ports, and assign the target groups. Trading raw compute savings for a managed ELB reduces the operational overhead of the networking layer. It is the enterprise standard because it allows your engineers to focus on application logic rather than managing infrastructure. The ELB functions as a central junction point, integrating natively across the broader AWS ecosystem. To secure your entry points, ELB connects with AWS Certificate Manager to natively bind SSL and TLS certificates for automated encryption termination. For operational visibility, the load balancer streams live logs and latency metrics into Amazon CloudWatch. At the network layer, Amazon Route 53 utilizes specialized Alias records to point custom domains directly to the ELB's endpoint without incurring lookup penalties. On the compute side, engines like EC2 auto-scaling groups dynamically register new targets to the ELB as soon as new instances boot up. For edge protection, you attach AWS WAF for application layer security, while AWS Global Accelerator routes incoming client packets over Amazon's optimized global fiber networks. This extensive integration fabric creates a highly automated, secure network boundary. Maintaining these connections reliably with self-managed software requires significant manual engineering effort. An ELB must continuously verify target viability using an automated health check mechanism, sending periodic HTTP GET requests to a specific file path. If a target times out or its application daemon returns an error code consecutively, a failure threshold is breached. The ELB detects this failure, classifies the target as unhealthy, and immediately stops routing client traffic to that specific node. If the instance recovers and then passes its consecutive health checks, the ELB automatically restores the traffic flow. This dynamic target isolation, driven by transport layer health checks, is the core mechanism that prevents a single instance crash from causing application-wide failures. To secure your compute fleet, you implement a three-tier isolation model. Your application servers reside in private subnets, completely unreachable from the outside world. The multi-AZ ELB is the only public-facing component, configured to allow inbound internet traffic from any source. This introduces a critical configuration challenge: securing the private EC2 instances without blocking legitimate traffic forwarded by the ELB. Exposing the EC2 instance's port 80 to the public internet is a vulnerability because it bypasses your load balancer's protections entirely. The correct configuration dictates that the EC2 security group must allow inbound port 80 traffic exclusively when it originates from the ELB's specific security group ID. Even if an actor obtains the private IP address of a backend instance, hypervisor-level packet rejection will immediately drop the direct connection attempt. By referencing security group IDs rather than static CIDR blocks, you create a logical security boundary, forcing all traffic through the ELB and attached security services. Under default configurations, an ELB distributes client requests using a round-robin or least outstanding requests algorithm. This random distribution breaks stateful applications, specifically when user session data, like a shopping cart, is saved locally in the memory cache of a single EC2 instance. To solve this routing problem for stateful architectures, you can enable active session affinity, known as sticky sessions. On the first request, the ELB inserts a specialized tracking cookie into the HTTP response header sent back to the client. Upon receiving that cookie in subsequent requests, the ELB overrides random distribution and locks the user's path back to the exact same instance. But this introduces architectural trade-offs. Sticky sessions prevent balanced fleet loads, which can lead to congested nodes sitting alongside idle hardware. Furthermore, if that target instance crashes or is scaled in, the user's bound session data is lost permanently. While sticky sessions are a useful patch for legacy software, modern cloud architectures prioritize extracting session state to achieve true horizontal elasticity. To summarize, managed ELBs provide robust SLA protections, high availability, and ecosystem integrations that are not easily replicated in self-managed environments. Continuous transport layer health checks and security group logical locks are the foundation of a secure, self-healing routing network. However, relying on sticky sessions for local state routing creates a fragile system that limits horizontal elasticity. The next logical challenge is designing a highly available, truly stateless system using EC2 autoscaling groups that can dynamically scale without risking customer data. We will explore that in Part 3.